welcome back. Now, in the last video, you learned about IMRT and VMAT and what it is and the rationale for it and how it's delivered on a linear accelerator in a modern radiotherapy clinic. In this video, I'm going to talk about how IMRT and VMAT plans are accomplished in a treatment planning system on a computer. So that will allow you to go from what you want, which is a dose distribution in the patient, to, in most cases, a sequence of the leaves for the delivery. All right, here we go. So throughout this video, I'm going to be referring to a case study here, this plan. So let me orient you a little bit. This is a prostate plan, actually post-prostatectomy. You'll see gold markers in there too. The blue here that I'm showing, that's the CTV, volume that you want to irradiate. And then there's some normal tissue here. Let me turn those on. So you got the rectum and what is that, purple, and bladder in yellow, right? Also, I can turn on the rectal wall here. We talked about that in one of the previous videos. Also, there's an expansion around here. The dark blue, that's the PTV, and non-symmetric expansion around the CTV. Okay, and then the femoral heads here, this is the bones on the side. So I'm going to start doing a simple plan on this case. This is not IMRT planning I'm starting with, but I think I need to explain this to understand IMRT. So I started with the AP beam, and then now I'm going to make a PA beam. And you can see that I can conform to the PTV. Let me make another angle beam over here. Let me rotate this a little. Let me turn on the femoral heads. And then let me rotate this a little bit. And you can see as I rotate, I can kind of pick an angle where I'm coming kind of between the femoral heads. You can see that in the beam's eye view on the left. I can pick sort of the optimal angle. This is kind of one of the things that you do when you're doing 3D conformal radiotherapy planning. You're picking the optimal angles. There's an opposed beam for that one. And then let's copy this other one, and then we'll rotate that guy around. So this is kind of the game you play. So you're picking best beam angles, you're conforming the MLCs, maybe you're adding wedges. I'm not going to put any wedges here in this simple example I'm doing. But this is the technique. So then you can conform them. So now they're all wrapping around the PTV. You got now, what is that? 1, 2, 3, 4, 5, 6 beams. I'm going to give them all some MU so I can calculate the dose, and then I'm going to calculate dose. Okay, so there we go. There's well, that's just the one beam, but now if I weight them equally, here's all the beams together. So there I did it. A simple plan to treat that PTV. You can see it's not very conformal, but this is what we call forward planning, meaning I decided for the computer how to plan it, how to make the beam shapes. Yeah, clearly this plan has some room for improvement. I haven't spent much time, but it's not very conformal around the PTV, so it doesn't wrap around the rectum. It's got high dose spilling out. The DVHs on the right, you'll see they're not very good. So this is the hope of IMRT, is that we can improve this. Now to do that, we need to address the issue of how do you get from a dose distribution over on the left to a shape of leaves on the right. And so that's the problem or the process that we call inverse planning. So given dose distribution that I know I want, how do I get a leaf sequence to give me an IMRT fluence? That's what I'm going to talk about now. So let me redraw this as a little cartoon so it's easier to talk about. Prostate PTV on the left, and here's let me draw the isodose line that you want and how it should conform around the PTV. So that's what I want to achieve, and if I were to achieve that, I would have a DVH that looks something like this. It comes over and it's nice and uniform, drops down as we've seen before, and then the leaf sequence corresponding to that, the fluence maps would look like this. So that's the ideal case. What about if it doesn't match that ideal situation? I deviated from it. Let me alter this a little bit. So let me redraw this isodose line. Now it comes this way, but it cuts into the PTV. It doesn't fully cover it. And so I've got a cold spot. So the DVH, I think you can imagine, would look something like this. It's kind of has a cold spot there. So you start to lose coverage. It comes down like this. Before, it was coming out like this with a more even, uniform dose distribution. So there's actually a cost or a penalty associated with deviating from that idealized dose distribution where you're covering the PTV completely uniformly. So you can write a mathematical formula for that, and that's going to be the basis for inverse planning. So let's spend a minute with this. What this is called a cost function, F cost. And the cost function is computed for each pixel in the dose distribution. That has each pixel has an index I, so I'm going to sum over those in the end. That's the sum. And what I'm going to calculate here is a deviation. So the dose in that pixel I and minus the idealized dose dm in that pixel. That whole thing squared, so it doesn't have a sign, and I multiply by some weighting factor, which tells me how important is that cost function for that particular organ that you're calculating. So, for example, if it's a PTV, maybe the W factor is very high for that because you want it to be very uniform in all the pixels. So there are other organs, at play here. So let's draw in the rectum behind this, and that will have a dose distribution within it, and it will have a DVH as well. So maybe the DVH looks like this. And then we're going to set a point here for this OAR. There'll be one for the PTV too, but I'm not going to draw that. But it's an objective and it sits in the DVH, and it says, okay, that I want the DVH for that OAR to be less than that point. In other words, I want to push the dose off of that OAR. And that's going to become part of the cost function as well. So now I've got two competing factors in the cost function. I've got the objective to cover the PTV with a uniform dose, and I've got this objective for this OAR. In other words, to keep the rectal DVH below that particular value. So those two are competing with each other, and it becomes an optimization problem where you want to balance those two objectives against each other. So you specify the weight for each of those, and given those weights, you can find what the solution is. So I'm going to not get into the mathematics of this very deeply. It's complex, and I don't think it's particularly important that you understand the deep details. But there are different algorithms, there are different ways of coming to the right solution. But the important thing is to understand what the goal is here and how it basically works. Once you set those goals, you can solve for this and get an ideal fluence for each beam of that IMRT treatment. So we've talked about that in the last video, what these fluences look like. So you might solve it and you might get this as an answer. We saw this in the last video. And once you have this fluence for each beam, then you can turn that into a sequence of leaves. And we talked about that in the last video as well, so hopefully that doesn't come as a surprise. So these then are the essentials of inverse planning, going from the dose you want to deliver to a beam that you can deliver. So in the remainder of this video, I'm going to run through a case example of how this actually works in practice. On that plan I showed you, I'm going to do an IMRT plan, and then I'll do a VMAT plan. This whole thing takes about 7 minutes, so you can skip this part if you don't want to see the details, but it may be useful. I've sped it up a little bit, just 1.5 times speed up from what the computer actually does, but we can work through this quite quickly. Alright, so here was the slice again. I put 5 beams on here. You see these 5 beams? So this is going to be an IMRT plan with 5 beams. And now I'm going to set up objectives. I add a physical objective. I'm typing in here. You can't see me typing it. But, this is for the PTV. So this is a minimum dose of 6840, and I put a weight of 100 on that one. Then I put a maximum dose of 7182, that's 5%. I put a weight of 1,000. I ran it. You see it's running. And the thing on the right, on the bottom that you're seeing, that little line, that's the objective function. Or I'm sorry, that's the cost function. And now you see the DVH that you achieve, and you can see it wraps around the PTV pretty well. I can actually improve this a little bit. I can add a fall off here. I'm adding a fall off into the body, and I can do a fall off, a high dose fall off, and a low dose fall off. And then let me run it again. Maybe it improves a little bit, but not much. But it's conforming that dose around there, and you'll see just in that short amount of time it did a reasonable job, better than my forward planning probably. But I could achieve some more rectal sparing. You can see this is the sequence of leaves that it came up with. If I scroll through the beams, here's what they look like. So this is deliverable. But let's see if we can do maybe a little better with the rectal sparing, try to drive this DVH down to pull the dose off, hopefully not lose the coverage in the PTV. So type in the rectal DVH. I'm going to put a max DVH. I can move the point around, but let me put it here at 6,000 and say I want to keep it 6,000, 20%, and 50 weight on the objective. Now it's running for iterations, and so there we go. You can see I might want to improve the PTV coverage a little bit. I lost too much in the PTV, so let me run it again, and now you see the PTV is improving, the uniformity, and so there we go. So if you look at this now, you'll see the dose is pulled off quite a bit off the rectum. You've got a pretty good DVH, or pretty good coverage in the PTV. You've got these little hot-ish spots out here. These aren't too high dose, so I'm not going to worry about those. And then you've got these sequence of leaves that you can deliver. So let me compare this then to the 3D conformal plan. We can have a look. So here's the two of them together. 3Ds on the bottom, IMRT on the top. You can see the DVHs, and it's sort of what you would expect, I suppose. The rectal DVH is a lot worse in the 3D plan. I didn't spend that much time on it. But the PTV actually isn't that much different, is it? It's uniform coverage in both cases, but it spills out more in the 3D plan. That's not really captured on the DVH, so I wasn't really not really visible on that screen. Here's the bladder, femoral heads. You can see pretty. Those are kind of different because I don't have beams going through them at all with the 3D. So, but I didn't try to spare them, and the IMRT probably could have. All right, now let's go look at a VMAT plan. Put an arc on here. You'll notice the collimator is rotated. We do that in VMAT to make sure the leaves don't line up with each other. And then I copy the objectives, and then from the last plan, and I'm just going to click Run. So there we go. You'll see it running. You'll see it takes a little bit longer because you've got more little beamlets to optimize. This is every 2 degrees per control point. It's going around. Control point is each one of those little segments. And now we have a plan. And looks pretty similar. These are the leaves. It can play this for you. So this is how the leaves would go when it goes around. And then we can compare it now to the IMRT. So I go over here. IMRT, let's see, is on the bottom. And you can see the DVHs and compare them. They look fairly similar. Here's the femoral heads, bladder, rectum's on there. And so there you go. So this is IMRT and VMAT planning as it exists today, at least. All right, so that concludes the basics of inverse treatment planning to achieve the IMRT or VMAT dose distribution that you want. I'm going to leave you with a little bit of further reading here. Again, the literature on this is vast. This is just a few samples. Something I didn't talk about in these videos about IMRT, VMAT, I didn't talk about how you QA the beams, how you do quality assurance to make sure that the IMRT or VMAT plan that you want to deliver is actually deliverable and achieved. So that's a whole topic, and I'm going to come back to that in a future video. But I think, to understand that, you're first going to need to understand about detectors and how those work and how measurement devices work. And so I can't talk about that yet, but it will come in a future video. So with that, it actually concludes the part of these part of these videos about treatment planning for photons. And now in the next videos, we're going to move on to other topics. I'm going to talk about electrons, then we'll get around to measurement devices and other topics. All right, hopefully this is helpful.